Hello and welcome to the final pre-practical lecture, the pre-practical lecture for experiment 3.
Brought to you by the University of Pretoria.
So where I want to start the conversation is with the concept of inorganic synthesis. And how do we uh, how do we know what we've made and how do we look at it and what is going on? What have we been doing the past few weeks and what are we going to continue to do the next few weeks? So let's say we start with some cobalt-2 species, hexa aqua cobalt in the 2+ state, and we react it with some reagents. Already, we can use our intuition to try and predict some products that may form because we know hydrogen peroxide is an oxidizing reagent, so we know cobalt will go to the +3 state. We know ammonia is a ligand that can coordinate. We know that these two things in solvent form, or once solvated, will split into NH4 plus and CO3 2 minus. So those are options that might coordinate to cobalt. So, replace the aqua ligands. So there might be an NH3 that goes instead of this aqua ligand. There might be a CO3 that goes in place of two of these aqua ligands. There might even be some H2O2s that coordinate in some fashion, right? So all of these are possibilities, right? So we can have 6 amines, for example, that just coordinate there with all of these being an oxidization. So from cobalt 2 to cobalt 3, and just some combination or other of new and interesting and different things. Okay, right? So essentially what this just is that we can use theory to predict reasonable or give reasonable predictions of what will form. Right? That's essentially what we've been doing. You don't really have to, I didn't go into any detail of why I predicted most of these. The point was just being, we could look at something and we can predict what's going on. Like you do in organic chemistry, you can also now predict for inorganic chemistry. But the benefit we have is when we do it experimentally, is we can also confirm what we have formed. Right. So we don't have to keep on predicting and say and argue or logically justify why we think something has formed. We can actually test experimentally if something has indeed formed. And that's what this experiment is about. We start with something, we do a bunch of things to it, and then we confirm whether or not things have formed. And that together is what is the basis of inorganic synthesis. That's exactly how it is. You react something, you form stuff, you confirm whether or not you've made it by a variety of techniques. So the pathway or the iterative process of inorganic synthesis, you start with reagents, you have some reaction or reactions, which leads to crude products. You will separate or purify with recrystallization or rotoevaporation or filtration or whatever, gives you clean products. You characterize those products with a host of techniques, which I'll get into now. And then you have a yield and product confirmation, right? So you have a yield, something that's formed, and product confirmation being some sort of technique that you use to confirm whether or not you've made the product. And then actually sometimes you can use this product you formed and react that again to form a whole host of new products. So some subsequent reactions on whatever you form. You'll also do that in this experiment. So you'll form first something and then you'll react that again in subsequent steps. So that's the iterative process, and then whenever you want to stop, you stop at this point, right? So essentially, how do we know that we formed something? Well, firstly, we can use our senses. We have an idea of what we're looking for. We're looking for something purple, and we're looking for something uniformly purple, and we know if we have purple and black or a mixture of yellow and purple and whatever, we know sort of what's going on, and we know what the reagents look like, and we know what the product looks like. We know we still have a mixture of those. We know we don't have clean products, whatever. The main thing, of course, is instrumental analysis, which is the point of this practical, is to introduce you to how we use instruments to test for purity and characterize our products once we synthesize them, to say that, yes, we confirm that we've made something. And of course, then experimental tests you've also been introduced to. So Like with the chromium prac, which we use the purity test with ammonia to see whether or not the polar one dissolved and the non-polar one did not dissolve. That was our test. So elaborating on instrumental analysis, in this practical we'll be using IR. It's usually IR or Raman. It's the same kind of wavelength. Raman is just an extension. It's more about the crystallinity of a product than what IR is, but IR has to do with the internal vibrations of structures. And we will use that to characterize and confirm our product synthesis in this prac. Some other things you might be aware of is NMR from organic chemistry, UV-Vis, you've done now, you know how we can use UV-Vis to characterize. And other things you might not be aware of is mass spectrometry. Mass spectrometry is essentially if we know how much it should weigh, so in other words, we know the molecular formula, we can, well, shoot our, or not burn, but we can quantify our product and see if the weight or the mass makes sense on a molecular scale to see whether or not we have the right amount of cobalt and the right amount of carbon and the right amount of oxygen as we predict in it. And that's what mass spectrometry is. And other things like XRD is like what I do, single crystal and powder XRD. But anyway, essentially, we can use instruments to see whether or not we have a clean product and whether or not to confirm we've made what we set out to make, you know, so the theory. So we predicted we have some reagents, we predict products. Now we've made the product. Do these predicted products and our experimental products correlate? Are they the same thing or are we wrong? You know, that's the big question we want to answer. Okay. So the point of this experiment is that trying to figure out what have we made. Characterization, meaning what have we made? So what are we looking at in experiment 3? In experiment 3, we'll be synthesizing these 5 complexes, which I've drawn here. Notice I've not drawn in any dashed or thick bonds. That's up to you. Just general structures here, just general line structures. And I've added the charges so long. We go through now again how I got to these charges, just so that everyone's on the same page. And essentially what we want to do is we want to firstly synthesize them, purify them, and then use instrumental analysis to confirm whether or not we've actually synthesized these complexes. Okay, so that's the point of the experiment. So our initial part is, how do we tell these complexes apart? Well, if we just give them a general glance, we see there are some similarities between them. So we can look, we give them a comparative characterization, that's what it's called. So they all have NH3 ligands, right? So this one has 6, this one has 5, this one has 4, 4, and 4. So that is the same. So whatever instrumental analysis technique we use IR, for example, so there should be an NH3 peak or peaks associated with NH3. Those peaks are going to be influenced by the other ligands in the inner sphere of the complex, right? Because that electronic arrangement or electronic environment is going to change depending on whether or not you have 1 chlorine, 2 chlorines, a carbonato ligand, a nitrido ligand. That all influences whether or not will influence the NH3 ligand's vibration. Okay, so that's the first way you can look at it. You can also look at the differences. So in other words, you can see, okay, well, we can look for cobalt chlorine differences. So if we see something with a cobalt chlorine, so something characteristic of a cobalt chlorine stretch or peaks characteristic of that, we know it's either one of these two and it won't be some of the others. Or, you know, something about carbon and oxygen or nitrogen and oxygen, we know it's associated with these two. Right, so that's how we differentiate between them. So you can list them, list the similarities, list the differences, and we will compare them comparatively. And that's what we'll essentially do, because it's very difficult to look at a spectrum and say directly, this is what it is. We usually use about 6 or 8 different techniques at the end to fully characterize a species on its own. But in this practical, because we sort of know what we're doing, we just want to confirm that it is indeed what we made, we start off with the answer and we just want to confirm that it is indeed the answer. So we'll do it comparatively. Okay, now, as promised as well, let's again just look at how the charges are formed. So cobalt is here in the +3 state in all of these complexes, right? So that we know. We know NH3 is an L ligand. So L ligands are neutral ligands. They just give two electrons through a lone pair that they donate in the bonding. So that it contributes nothing to the charge. No worries. This carbonato has a minus ligand and a minus because this is 2x moiety or 2x fashion ligands that bond to one another or to bond to the metal there. So in other words, this is 2 minus, so we have cobalt 3 plus, 2 minus gives us 1 plus. Chlorine is also an X ligand. I'm really bad at this. So we have a minus here, cobalt 3 plus minus 1 gives us 2 plus. Only L ligands, so we have cobalt 3 plus gives us 3 plus. We have minus minus, so cobalt 3 plus minus 2 minuses, or minus 2 gives us 1 plus. And then these are also X ligands, again minuses, 2 plus minus 2, 3 plus minus 2 gives us 1 plus. Okay, so I hope you know now how to assign these ligands by now, how to assign L and X, ligand moieties, and get the charges. Okay. Moving on to the characterization. So let's look at these three nice and comparatively. So the hexaamine, and the pentaamine, monochloro, and the dichloro tetraamine ligands. So we see the charges differ in 3 plus, 2 plus, 1 plus, and also the number of chlorine ligands in the inner sphere increase, right? And one thing that you should notice with this is because they have different charges here, it also means they will have a different number of counter ions. Remember what a counter ion is? It's an ion that needs to counter the charge of the ligand of the complex itself. So for example, it will either be nitrito or chlorido ligands, or not ligands, anions, chlorido or nitrito anions, depending on what the practical guide, we say there what it is exactly. So an NO2 minus or Cl minus, so there will be 3 Cl minuses, for example, with this one, or 3 NO2 minuses. I can't remember exactly which ones it is actually, and it's too deep into this video now to quickly go check that. Oops. Anyway, which crystallize alongside this as the counter ion for this species. This one will only have 2. This one will only have 1. Right. That is something you need to mention, as well as the chlorine. So there's chlorines in the inner sphere increasing. Okay. And how does that help us in the characterization? Well, that means firstly there's going to be an incremental color change. So we could have used UV-vis. In other words, this might be a low spin complex. And the more chlorido ligands we have in the inner sphere, the higher spin the complex becomes. In other words, the peak shifts a bit more upfield, more energy intense excitation is required. So you see a difference in the absorption frequency or the absorption wavelength. Differences in IR stretches. We could see the appearance of a cobalt chlorine stretch and the intensification of a cobalt chlorine stretch in the IR spectrum. We could also see a weakening of the NH3 stretches, because remember I said whatever you change in the electronic environment here is going to influence these ligands. So however they interact in the IR spectra or appear in the IR spectra in this case will be different to how they appear in this case, will be different to how they appear in this case, because chlorine is usually going to take more of the electron density with them, making these stretches less strong. And then finally, what I want to get to, where I started talking towards with the anions, with the different number of anions, we can have a change in physical properties, specifically in the solubility and the conductivity. This is completely non-polar. This one is polar. This one again is sort of polar. But more importantly, conductivity. Because conductivity is something that has to do with ions. And if you have ions in solution, then you have conductivity possibilities. So you see these are all ions. And this one will have 3 counter ions. So in total, we'll have 4 ions. This one will have 2 counter ions. So in total, we'll have 3 ions in solution. So we only have 1 counter ion. So we'll have 2 ions in solution. And if we say conductivity is proportional to the number of ions that is able to carry charge, and we were to say measure the conductivity of these complexes, what would you expect? You would expect the one that has more ions to have a higher conductivity ability than the one that has less ions. Okay, and that actually correlates with the Werner and Jorgensen argument and how they sort of fought for years about, like, where is the chlorine actually? Is it outside the complex? Is it an anion, or is it an inner sphere ligand? What is it in fact? But anyway, so more on conductivity. So conductivity means that you need ions to have some sort of conductivity. So water has this amazing ability to polarize itself and to split into its OH and H3 plus constituents, and then allow it to conduct. So in other words, with all the alkali metals, or in the presence of CO2, for example, it can form ions, and that can be used to induce electric flow. And then depending on your mental state, then you can have some interesting times. Okay, so like I said, conductivity increases with the number of ions in solution. So that's what we want to test. So count the number of counter ions, and then you'll be able to see which one is which, because we expect this one to have 4 ions in total, 3 counter ions plus this is an ion, 2 counter ions plus this one, 1 counter ion plus this one. And then if the ions are charge carriers, the more they are, the better the electric flow will be. Okay, so that's what the conductivity part is of this experiment, is, or how that correlates or fits into it. So we have the characterization as well as the conductivity measurements. The conductivity measurements is also a confirmation of where these ions are. Are they part of the complex, or are they counter ions? Okay, you need to read that prelude or introduction to the experiments a bit carefully to understand what Werner and Jorgensen were arguing about initially. Okay, so let's talk about the fundamentals of IR radiation. So to get your brain into the mode of thinking about IR, so let's briefly, so we start with the brief concept of electromagnetic radiation, and just remind ourselves firstly of the electromagnetic spectrum. So I've drawn you a nice, beautiful electromagnetic spectrum here. And remember, firstly, so radio waves are too weak to interact with matter. I mean, otherwise we would all be boiling with all the radio waves moving through us. So radio waves don't interact with matter. They don't cause anything. Then you should be aware that microwaves induce rotation. So that's how a microwave heats up your food. It rotates the polar molecules within a substance, and that excites its rotational levels or excites the molecules through different rotational levels and moves it to a higher energy. Because it has a higher rotational energy, it occupies a higher rotational energy level, it has a higher temperature, because that's the way around it works. Not because something is hot, it has a higher energy. Because it has higher energy, it is hot. Anyway, you'll learn more about that if you do honors or third year in physics. Well, right, anyway. So microwaves do that. And then what we are interested in is IR, because IR causes vibrational motion. So in molecules, IR causes things to vibrate. As you know, UV can cause bond breakage. That's why you can get cancer if you lie too long in the sun. It destroys your cells, as well as other things. And then, of course, finally, X-rays and gamma rays can ionize substances, remove outer shell electrons, or even gamma rays can even remove inner shell electrons. That's why you die when you get exposed to these kinds of things, because it ionizes you. Okay, but we want to focus on IR. So that's just a reminder of how electromagnetic radiation interacts with matter, how everything interacts with it, and specifically IR causes vibration. So vibrating of atoms in a molecule is connected with IR. So we need to correlate those ideas with what we want to look at in IR spectroscopy of our complexes. So a bit more on molecular energy levels. So what you've covered thus far in your life is the concept of electronic energy levels. So a transition between one electronic energy level to the next, so that's typically a UV transition. So you have some sort of UV energy, and that takes a molecule from one energy, or an electron from one energy level to the next. So essentially moving the molecule from a non-excited state to an excited state, essentially, which is why we allow bonds to break and whatever. So those are called electronic energy levels. But within these electronic energy levels, we actually get rotational and vibrational energy levels as well. So we call them ρ-Vib vibrational, ρ-Vib energy levels. I just realized I had something here. So electronic levels is usually UV with high energy. So that causes molecular energy level transitions. But within these molecular energy levels, we have these rotational vibration energy level transitions, which we can have. And remember, we said in the electromagnetic spectrum that rotational energy, so microwave energy, is less than vibrational energy because it came before that. So rotational energy is your lowest energy interaction with matter. Vibrational is your second lowest, which can be induced. So illustrated as here. So you maybe have 2 vibrational energy levels, but you have 6 rotational energy levels within 1 electronic energy level. You see, so they're all sort of subsets of the same larger set of one another. You can look at molecules as sets, and if you look at group theory and whatnot, it's a very interesting field. Anyway, but essentially what we want to get to is the fact that we can use low energy, long wavelength IR to excite energy level transitions for a molecule and make the molecule vibrate, like this one's been waving for the past 20 minutes that I've spoken about transitions here. So we can induce this kind of motion or various types of motion in a molecule through this type of excitation. So essentially what IR does. Exposing a molecule to specific IR radiation induces some sort of motion, vibrational motion. So just as a very short example first, so CO2, just some ideas of the type of motion that you can get. So you see the different peaks here or signals in the IR spectrum correlating to a wave number, so not wavelength, wave number. So you see the unit here, so you easily can translate it to wavelength, but just be cognizant of what the units are. And you see we get a variant type of motion. This is quite symmetric, this is asymmetric, this is like a waving motion, and this all leads to different kind of stretches, right? But how is this at all useful, really? I mean, it's like, and how do we know even it looks like this and whatever? So this is like this is computationally designed. I mean, I didn't thumb suck it and knew how these molecules work, or how they wave or vibrate. But essentially, how can we use the spectrum to help us identify molecules or complexes, or at least ligands within complexes? Right, so that's our big question that we will discuss with a bit of a more complex example. And our more complex example is benzene. So you can see there's a bunch more peaks in this spectrum. And the first thing I just wanted to remind you of is, of course, that wave number is frequency. So lower wave number means longer wavelength, because it's the inverse of wavelength, means lower energy. And then we search in the lower energy region, or the longer wavelength region. So the lower wave number region is what we call the fingerprint region. So that's between here about 450 per centimeter to 1,450 per centimeter. So we call a fingerprint region in IR. So that is a region which is unique to a specific molecule. So once you know what the IR of a molecule looks like, you can use that knowledge, or what those peaks are. So these are for whatever peaks these are assigned as. Then you know if you see these peaks in these order and they have these characteristic stretches, you know you're probably looking at benzene. If you see all of a sudden there's another peak here, then you know it's not benzene. And IR isn't a very specific, you don't usually use IR on its own, you use it in conjunction with a bunch of techniques, but we will use IR in this method. So we will look at specific regions and apply our knowledge of what we're trying to look for and say, are we seeing that? Okay. So getting to the point of what are we looking for and getting to see that, you will see this figure in your Prac guide. So this gives you a list of where do we expect specific kinds of stretches, or, you know, the region. So where do we expect the bond of carbon and nitrogen, or oxygen and hydrogen, or nitrogen and oxygen, specifically the carbonyl group, for example. What else do we have? We have NHs, a lot of NHs in these molecules that we look at. You know, so where do we expect those stretches to be? So in other words, if we look at an IR spectrum and we see a stretch in this region, we can assign it to that moiety of the ligand, for example. So if we look at our complex and we see, oh, one of them has a peak there, then we know it's the one that contains a carbonyl, for example. Okay, so that's sort of how we'll use the IR. It's not, like I said, it's not the definitive holy grail of characterization techniques, but it is a way of getting an idea, or at least what you can use, right? And like I said, in the fingerprint region, each of them should have their own unique bunch of stretches that we can use to say each of them are different complexes. If one of them have exactly the same spectra or spectrum here at the beginning, set of peaks here at the beginning, between 450 and 1450, then you might start asking, do you actually have perhaps a mixture of products, or what's going on there? So remember, that's the only point of the fingerprint region, is just to say that the product is indeed unique. And if you know how the spectrum is supposed to look like, then you can match it to that. If you have no idea what it is supposed to look like, then you use this to assign peaks to specific stretches. So in other words, to say that there must be a CH present in the molecule, or there is a C triple bond C present in the molecule. That is what we think there is one. Or do we expect there to be one? Yes. Do we see a peak there? Yes. Then there is one. Okay. Right. So let's look at some theoretical spectra. Let's start with the hexaamine complex, which you will synthesize. And essentially, the biggest stretches, the only stretches that you'll see here is of that of an amine ligand, so an NH3 ligand. And the calculated spectra for that, so I say calculated theoretical predicted spectra, contains either an NH stretch or an NH bend. So these bend and stretch just means that, you know, it either has a stretching motion or bendy motion. And we can see that there are peaks, these little doublets. You might ask, why are they doublets? I mean, the answer would give you 2 seconds to theorize by yourself. Why are there two different peaks sort of for the same motion? I think because there are different molecules here, so they either do it all together or they might not do it all together. And that gives rise to something that is just slightly different, right? Okay, anyway, and then we get these two characteristic peaks. So you see there are different peaks here that also are present. I'm not quite sure what they are. They might be cobalt nitrogen peaks. There might be different variations of what they are, but the ones I wanted to look at are, for example, what is an NH stretch? You know, so remember I had on the previous slides, or in that figure, we had a point where we said NH, and then NH also appears at a few other places. So this is how you go about it. So you say, okay, that's NH, that's NH, an NH bend, but this is the NH stretch, and you just assign those peaks. Okay, but because we want to do, so I've continually been speaking about comparative analysis, right? So I've been saying compare apples with apples. So ones that have amines compare with the other complexes that have amines, right? So let's say, for example, we swap these two amines for chlorines. How is this going to affect our IR spectrum? So, firstly, what you should expect, I mean, if you don't have 6 of these making noise, well, bending or stretching, you should expect your peak signal to decrease, right? So, essentially, we still have the amine stretch, and the bend is still present, but we have considerably less. So, in other words, that's what the effect of the substitution was. We've just lost out on the intensity has reduced because we now have 4 instead of 6 of them making noise, if you want to put it like that. You see again here, this region has changed because we're working with a different molecule. We're working with a different complex. So its fingerprint region is unique to whatever it is, right? One thing we do, however, not see is any cobalt chlorine stretches. I don't see them actually in this spectrum. You don't have to worry about that. You don't really have to identify them. You might be able to see them in your experimental spectrum. So that's something you can also look for, is because that's unique to this structure, right? There should be cobalt and chlorine stretches. This one will have cobalt nitrogen stretches, but the previous one will also have cobalt and nitrogen stretches. So it's not really giving you any interesting information. But the difference between the previous one and this one is this one has weaker stretches. The intensity has decreased, right? And maybe your experimental can have the cobalt chlorine stretches. The theoretical one does not. That's what I'm trying to convey here. Right. So let's stay with the idea of the 4 amines, but now let's go to the one that has that carbonato ligand. So here we see the carbonato ligand, so still 4 amines. So we expect those intensity peaks or those amine stretches to be quite weak. But what do we expect now to appear? Remember I emphasized earlier in that figure that's in your Prac guide that there is something called a for goodness sake, a carbon-oxygen, a carbonyl group stretch. So C double bond O stretch. There should also be CO stretches, right? And even cobalt-oxygen stretches should be visible. So focusing on the CO stretch, you can see there is now a peak here next to our NH bend. There is a very strong peak, actually a fundamental stretch. So a fundamental stretch is actually just the one that's the strongest in the spectrum, so the one that's I say the tallest, but the one that's the longest magnetite. That's growing from the top. That's called the fundamental stretch, and that corresponds to this CO stretch that you see, right? But we still see our NH stretches, our NH bends, and you see once again our fingerprint region has changed because we're working with a different complex, right? And you can go search up what is cobalt oxygen and cobalt carbon oxygen single bond stretches, which of these peaks are what, right? So another word for fundamental is also, of course, characteristic. So fundamental characteristic stretch, which is unique to this structure, very unique to this structure because it's the only one that contains a carbonyl. So you know how to look for that in your experimental spectrum. And what I've tried to show you with these theoretical spectrums is exactly how you would typically use IR. You would look at different spectra of either different molecules, or you would use things like your starting materials and say, does your starting material and your product's IR spectra differ significantly? In other words, can we definitively say that we've indeed synthesized something new, or is it just a mixture of the starting materials actually what we're seeing? That's the question. Is it something that has now formed a complex, or is it just a mixture of what we started with? Okay, so that's why I say look for regions that change significantly between the different complexes, because that results with changes between the complexes. So not only just the complexes, between the complexes and the starting materials, and the differences between the different complexes, because they might have C double bond O characteristic stretches, they might have NO double bond characteristic stretches, they might have NO, they might have CO, they might have cobalt chlorine, they might have the NHs which differ in intensities. So you know how to look for them. So like I said, make a list, check it twice, and then you make a list of what you expect to see and how you can do this comparatively. Okay. And then from there on, you can start identifying things like contaminants, so meaning starting materials, byproducts, or isomers. So using other experimental spectra, using the NIST library or reaxis. You know how to use reaxis by now. Draw the structure, look up its IR spectrum. You know how to do that. Well, NIST is also a very nice one. Then you can get it into Excel form and you can include it very nicely for yourself. To look up these things. But I must warn you, I know the first time you try to analyze IR, you try to analyze every peak. But you've noticed by now, I sort of just like, I look at, ooh, these 3 peaks, and I talk about them, and then I say, yeah, there's a region there, and then I move on. That's exactly how you need to look at IR. Because you're going to make yourself crazy if you try to analyze each peak. Because sometimes you're not sure. You're really not sure. You really just don't know. So the point is you're looking for your characteristic peaks, your fundamental peaks. You're looking for the differences, which you can explain. And really, by the point of that when you've really started explaining and you have about 4 or 5 peaks identified and explained and really rationalized, I mean, you can stop. That's the point. We'll go into more detail in the post-practical lecture of how to analyze an IR spectrum. I'll show you nice in detail. But for now, don't try and analyze all the peaks. Don't sit there and have a list for each of them, because literally you'll go off your head. But maybe it's good. Maybe it's good to have a breakdown at age 20 ish. So maybe go try analyze all the peaks. Anyway, cool. So that's all on IR. More in the post-practical lecture. Let's quickly look at our experiments. So the actual synthesis, some notes on that. Right, so we are synthesizing these 5 complexes. I hope that's quite clear by now. And they each have their different experimental numbers, which you can read up in the Prac guide of. And then what we do is we measure the IR and the conductivity of each of these compounds, and we compare that to one another to distinguish them. And we also inspect their crystals under the microscope. So I provide you with some images of the crystals under the microscope, and you can use that to distinguish. In other words, you're inspecting crystals, you use the color, you use the morphology, you use the shape. Well, morphology and shape is the same thing. Their texture, do they clump together? What in generally, just what you see. That's how we describe crystals. For example, it's a brown needle-like crystal with a rhombohedral shape that clumps together and it's a fine type of crystal. Whereas the other one can be maybe hexagonal and rough and does not clump together, and it's purple, just as an example. So that's how you distinguish between them, and you get the similarities and differences. Right. Okay, so ion conductivity, and then just a physical inspection using the sensors, because remember, we do use observational chemistry as well. Okay, so that's in essence what we are doing here. And just to explain how the experiments fit together. So the only experiment that does not rely on experiment 1's success. So experiment 3.1 is very, very crucial. So if you mess up here, then you will have to redo it, because you need about 4 grams at least of experiment 3.1 for your subsequent synthesis of each of these. So from experiment 3.1, you need to synthesize experiment 3.2, experiment 3.4, and experiment 3.5. So you'll be using a gram each here. You can read it in the practical manual. And of course, in principle, you need a gram of this over, because in principle, you do IR and you do things. Even though you won't be doing that yourself, the data has already been collected for you. But, in principle, you need it. So you need 3 grams, but you need 4 grams of yield. Okay. And the only experiment that you start with cobalt chloride is experiment 3.3, which you make the hexaamine ligand or hexaamine complex. So that's a separate synthesis. So that one you can breathe a little, but the rest of them are all reliant on experiment 3.1. Okay. And yeah, that's essentially it. So that's how they all fit together. 3.3 is on its own. And a final thing I wanted to remind you of, oh yes, remember when doing calculations of yields and for how much you need, or it's given to you in grams and whatnot, remember the molar mass of a complex contains the counter ion. So whatever the counter ion is crystallized here, that counter ion is contained in the molar mass of your crystal structure, and that is used to calculate the number of moles from whatever. It's not just the complex as you see it here with the charge. It's always the neutral species. Remember, neutral species have molar masses, right? Okay, not just ions. You never have, so if you have sodium chloride, for example, is that you don't just take the sodium as the thing that has as the molar mass. You take the sodium and the chlorine. You take the sodium, which is the plus, and the chlorine, the counter ion, and you get sodium chloride's molar mass, and from that you calculate the number of moles. Right, okay. So that's all I wanted to say here. Good luck. I'll see you in the post-practical lecture. I hope everything makes sense by then. Please now read the practical manual, watch the experimental videos, and I will see you in the lab.